Hey, what's going on? This is a quick update to the progress of the Workbench controller project. I know in the last video I said hopefully the next one will be the finished product, but this time I'm really close. But it's been long enough since I've had an update, I figured I would just post an update. Plus, it'll make all my videos a lot shorter if I do updates more often versus my really long-winded 45 minute to hour long videos. So anyways, I'm going to try to make this quick. Last time you saw that I already got the LCD mounted into the panel and I had it fit perfectly up to the right side of my instrument rack, and it works great. This is the first time I've actually powered it on since I mounted it to this board. Front looks all neat. You should see the back. I'll show you the back in a second. And over here is where the IR sensor is, and all I did, obviously this is just a really thin, I mean it's like this thick. It's a super thin like plywood. The problem with that is that it's so thin I can't screw stuff to it from the back because the screws would poke through the front. There's just no way to do it. So I kind of scratched my head thinking, damn, am I gonna have to put a bunch of holes in the front to put screws through from the front to mount stuff to the back? Well, what I decided to do, I'm really vain about stuff like that. I really want it to look nice. I don't want it to look like some, slapped together project. I want it to be something I'm proud of. So, anyways, here's the wiring on the back. What I did, LCD obviously is panel mounted, so that's pretty simple, and you already saw the screws for those. But I took a couple little blocks of wood I had laying around, cut it into smaller pieces, and then I glued it to this using wood glue. Let's see, where's the bottle? This stuff. Used some wood glue, clamped it overnight, and then now I have something thick enough to put screws into. And then, there's stuff sticking there, there's different solder blobs and junk sticking out the bottom of the Arduino board. So I have this really dense, it's kind of like memory foam almost, but probably, well, actually it's really similar to memory foam. Maybe it is memory foam. I ordered from Hobby King. It's a Chinese RC like hobby website, but this stuff's super cheap. You just have to wait 2 to 3 weeks for the stuff to show up. And I thought it was going to be the super soft memory foam they used for the old AM/FM radios, where you'd wrap the receiver in it because the gas engines would vibrate and it would cause interference. So you had to wrap them in this really soft plush like latex foam. I thought I was ordering the same stuff, but when it got here I found it to be a lot thicker, but I've already used it for like 10 different things, so I'm really glad I bought it. It was super cheap. So anyways, I cut a piece of that the size of the Arduino and then put it underneath so there's a little bit of cushion. That way when I screw it down into the wood, it's not going to put too much pressure on the Arduino from the bottom being uneven. And I did the same with this back little breadboard back there. What that breadboard is, it has female headers, and on that I put the real-time clock because it has male 0.1 pitch headers on it on its own little breakout board. So I plug that into there. It also has the 2 male pins that I plug the BEC into. BEC is basically another term for a buck converter, basically a DC to DC converter or switch mode converter, whatever. There's so many things to call them, but in the RC world they call them BECs. And for all you people who aren't into RC, I'm going to tell you what, these suckers are handy and they are cheap, much cheaper than you'd find ones that are not for RC. So they're called BECs because it stands for battery eliminator circuit. And basically you feed anywhere from like, probably like 5 volts all the way up to like 36 some volts, and it'll output a nice clean regulated 5 volts. And they're actually usually really good, really solid 5 volts too, because these are usually used for receivers and such. And if you're flying, your $1,000 RC airplane, and then if your converter droops too much and then your receiver flakes out and you crash it, that's no good. So these things are usually built to be pretty stable. And actually, the reason I'm using this, because you're probably wondering, hey, that's a PC power supply, isn't it? Yes, it is. And those red wires actually have 5 volts on them. The problem is that thing's drooping like crazy. When measuring the voltage at the actual Molex connector, it was almost drooping down to 4 volts. So that could actually speak to the quality of the power supply. It's a cheap, I don't even remember the brand. It was a cheapo though. Obviously it's way overkill for powering this project, but the only other options I could find are laptop bricks that happen to be 12 volts instead of 19 or whatever else they usually are. The problem with those is that they get really hot and there's no active cooling, and it kind of worries me. So I figured I'd rather get something like this. Surely something like this with a very tiny load that I'll be putting on it will last forever. So, anyways, yeah. After measuring the voltage on the 5-volt rails, it freaked me out. So that's why I got the BEC. And it just has wires coming out of both ends. Thick wires that coming out of one end are the source, which I have plugged into the 12 volts from the Molex connector, and then it's a buck converter basically, so it converts it down to regulated 5 out. And that actually has a Futaba connector on the other end, which basically is a female. It's the same pitch, almost identically to the 0.1 inch pitch female headers. So basically, I just slide those right onto the 0.1 pitch male headers, and boom, perfect fit. And that's where the 5 volts goes. And then I have some wires going to the Arduino shield to get the I2C rails over, as well as the 5 volt and ground. So all the grounds are tied together. And obviously the I2C has to get to the LCD also, because it's a parallel LCD, but I have basically it's a shift register, but Adafruit calls it an LCD backpack. It lets you communicate to it using I2C, and then it does the heavy work to run your deal. So technically you only need 2 pins other than the power pin. So that helped a ton, because I have this shield itself. It's a PWM shield. It uses I2C. LCD uses I2C, and the real-time clock that I'm using is I2C. So I have all those sharing 2 pins, which is freaking awesome, because there's actually, I don't know if you can tell from all these freaking wires, despite this being a not too complicated of a project, the wires are just piling up. And I'm going to show you kind of like a block diagram / schematic hybrid that I drew up, just to make sure I'm not forgetting anything important power-wise. And there were a couple little places I forgot. Oh, now that I'm not powering this from the computer, I need to do this. Now that I'm not powering it from my bench power supply, I'm going to need to do this. There's some things I had to figure out, and doing the block diagram really helped. So I'll show you that in a little bit. And that actually, when you see how much stuff is on there, you really realize how many components and parts there really are to this. So there are a lot of moving parts. So what else is there? There's where I glued the IR sensor there. Obviously that's the main input, user input is the IR sensor. So if it's not in a good spot and I can't reach it, then it's going to be frustrating and annoying and pointless. So what I did is wrapped it in heat shrink and then super glued the heat shrink to the wood. And I don't know if you know, but wood takes the super glue really well. And the reason I use the heat shrink is so if I decide that's not a good spot, I need better reception, what I can do is just carefully cut the heat shrink off, and then I can put new heat shrink on and then re-glue it somewhere else. So that's just to make it so it's not super permanent, because I don't know if you've tried to remove super glue before. Even with debonder, which I have, it's still impossible to get off of stuff. Oh, and this board back here, there's one other purpose that I didn't mention. It's got a logic level MOSFET on there. So that's what I use to low side switch the solid state relays and the fans. But, oh, actually, that's what I didn't mention. So I haven't I haven't touched this for a while. Since I mounted the LCD, I haven't powered this on. And between then and now, daylight savings has passed. Oh, excuse me. So, the time was wrong. It was an hour off. So I was like, oh crap, I really wish they would get rid of daylight savings. Really annoying to me, but I knew that I could just compensate for it in the code. Luckily, the real-time clock also has the month, the day of the year, all that good stuff. And actually some other handy stuff like Unix time. But Arduino's got its own kind of version of that. But instead of Unix epoch, it uses Arduino turn-on epoch. Whenever you turn the Arduino on, the time starts counting. So I use that for most of the timing, like for the power outlets. And the good thing about that is that it's not dependent on the real-time clock. So the real-time clock the battery could die and I could stop telling time and my timers would still shut off safely like they should. So anyways, how I compensated for it, I was only pulling the hours, minutes, and seconds. And so what I had to do is also pull the month and the day and dump them into variables and then just check if it's after March 8th or before November 1st, I think. Then it's daylight savings, and we add 1 hour to the hours. And if not, then we don't add an hour. So that is basically how I did it, and it works. So it is indeed 4:13 a.m. according to my PC. So that was a little frustrating, and if you do anything involving time with your project, you should probably keep that in mind. I luckily notice now, because it would have been a huge pain to have to plug this stupid thing back into the computer a year from now, or in November, which is not a year from now, but it's getting close to a year from now, and have the time be an hour off and be banging my head against the wall. Like, damn it. So I'm actually glad it happened, because I was able to fix it while the project is out on the bench and easier to work on. One other thing, I have this button here. It looks like an ordinary push button, but there's two cool things about it. One, it's latching. The second part, it lights up, but that's not super important. This one just lights up white. But I thought when it's on, I'll have it light up white, and when it's off, it won't. But weird thing is, this one doesn't actually have a current limiting resistor built into it, so you gotta use your own. So either way, what I liked about it, I have some other panel mount buttons, but they're for really, really thin, like plastic panels. Obviously, it's thin plywood, but for enclosures, it's actually kind of on the thick side, and this gives me, look at how much thickness I could have. So this will work perfectly. And what I'm going to use for this, I guess I should have said, you're probably still wondering, okay, great, it's a push button, what are you using it for? I'm going to hook this up to these guys. This is coming from the power supply. If you've ever built a PC or you know anything about computer power supplies, the green wire is the one you short to any of the black wires to turn the power supply on. So I'm going to hook these up to the button, and then that's how I will turn the project on or off. Now you're saying, hey, it's got time, wouldn't you want to leave it on? Yes, I will be leaving it on all the time. I just would like a way to turn the project off if something goes awry. If I see some smoke coming from behind this panel, or if I start smelling something funny, I can just reach up and turn it off and then try to investigate and find out what went wrong. Because not having a way to turn your project off other than crawling under your workbench and unplugging it is kind of sketchy. So this will just be a button that'll be there if I need to use it. So still haven't decided where I'll put it, probably all the way at the bottom corner of this panel, so it's kind of out of the way and I don't accidentally hit it. So that's an extra wire I'm going to have to run. It's actually pretty absurd how many wires are going to be running to the back of my workbench. So it's going to be kind of crazy looking. Another thing I didn't account for that it's one of those things you just don't think about. So you saw one of my previous videos that I decided to use USB as a modular connector to plug into my little power distribution solid state relay box thing, which is fine. And oops, sorry, I kicked the microphone stand. it worked great because, you know, it has 2 power pins and 2 data pins, and I can use the 2 data pins as the signal pins to turn the solid state relays on or off, and then one for ground, and then the other one was a free pin that I could use for like turning the fan on. What I should have done is done high side switching, but I decided to do low side switching, and that's what that extra MOSFET on that very back breadboard was. That's so whenever one of the relays turns on, I also in the code turn the MOSFET on, which low side switches the cooling fan for these solid state relays. The problem with that is I still have to send 12 volts to the box, so that takes up the 4th wire, and then there's no 5th wire in a USB cable to send the current return path for ground, basically. So what I decided to do, you know, if the fan's on, that means one of the solid state relays is on. So I let the solid state relays and the fan all share the same ground, the low side switched ground. So that way I can fit everything I need in just 4 wires. That way I can continue to use the USB, because it seems stupid to use something elegant like USB and a nice panel mount USB female jack, and then all of a sudden I need a 5th wire and I have to like drill a hole through the thing and just run it through. That's just sketchy and not elegant. So luckily it was able to drive the fan and both relays at the same time without a problem. So I'm sure the solid state relays used like, I'm sure it's not even 10 milliamps for that thing to turn on. All it is a little LED, so it's probably, actually, yeah, it might be. It's probably 10 to 20 milliamps for those to turn on. And then the fan, I think, is like 50 to 100 milliamps, so it's nothing at all. Not a problem for those to all share one common ground wire. Especially when you consider USB cables are used to do 2 amp charging on a lot of these new tablets and phones, my phone included. So if it can handle 2 amps at 5 volts for my phone, surely it'll handle, 200 milliamps total. I really doubt it would be any more than that. I didn't bother measuring, but yeah. I'm just trying to mention the little pitfalls, so if and when you do a project, it might be something that you can look out for and learn from my mistake, maybe. I'm using a female Molex connector to feed power to the entire project. So this is basically the 12 volts that goes in, and the entire project is powered off of here. And obviously the 5 volt parts are powered from this BEC, which is tied to the 12 volt in. And I think that's really it. All I have to do now to finish this, I still have to mount that guy to the bottom of my workbench, but that's easy. That's just, I haven't done it because the rest of the project's not done, so there's no point in me mounting it. I guess there's one thing I haven't showed you. Let's see. So as you can see, this fan is not spinning. So I don't think you can see that anyways, but I'm gonna turn that outlet on, and obviously the work light I have plugged into there I was testing earlier, but the fan kicked on. So now if we turn that off, you should see the fan stop right now. So see, it's not spinning. So yeah, it works well. Just a quick demo of that. All I have to do is drill 2 holes and run all the wires through the back, get the panel mounted up top. It's obviously 4 in the morning. I should be in bed, so I'm not going to do any drilling. I'm just going to render this video and then go to bed. But tomorrow, assuming nothing comes up, I'm going to get everything mounted up there and the project will be done. I can finally move on to other videos, do other stuff. Tons of videos I want to make, but obviously this is wasting a ton of workbench space, so yeah, it's not ideal, and so I want to finish this before I really get started in anything else. That way there's plenty of room to work on it, and it just won't be a mess. I hate clutter. It just drives me insane. So it's really easy with this kind of hobby to get cluttered. So Well, there we go. A quick update turned into 21 minutes. But hey, at least this is pretty much done. I just showed you how I did everything. The next video hopefully will just be a demonstration of the whole thing while it's mounted, and you can see how pretty and neat and tidy it is. So now I guess I will show you I don't want to call it a schematic. It's not quite a schematic. It's more of a block diagram. Wiring diagram. We'll call it a wiring diagram. That's close enough. It's basically more of a, well, I don't know what to call it, but it's a wiring diagram. I think would be the most accurate thing to call it. So let's take a look at that. That way you can just see how there could possibly be this many wires for such a somewhat of a simple project. Okay, you have to excuse the crudity of my schematic. I'm hesitant to call it that, but basically it was when I went to mount everything to the back of that plywood and get all the wires tidied up. You know, when I was working on this, the Arduino was being powered through the USB cable, and the 12-volt portions like the LED lights, the PWM controller, everything else basically was being powered by my my Workbench power supply. Sorry, I'm really tired. But now that it's going to be powered off its own power supply, I wanted a way to be able to make sure I don't miss anything, because I actually did. So anyways, I'm just going to show you. This is obviously where the entire project will plug into the wall. This is the power supply that you saw sitting on my bench. So obviously I'm using a 12-volt rail out of the power supply. So this blue wire right here is the 12-volt rail that I'm using to represent the 12-volt rail, so I can see what else plugged into it. And then this is the buck converter, or the BEC, battery eliminator circuit. Actually, I never explained why they call it that, really quickly. Most RC planes and cars and such had a big beefy battery, high current for the motor, and then they had like a lower voltage battery for the receiver and the servos. And then people realize it's too big of a pain in the ass to have multiple batteries. They're like, why don't you use a buck converter, step down the voltage from the main battery, and then have it power the receiver and all the supporting electronics. And so that's where those came from, and that's why now you can get those for just like a couple dollars from hobbyking.com or any other Chinese site. You can get them stateside, but they're going to be probably $10 or $15. They'll be marked up, but you can get them quicker that way. But anyways, and and then they're actually like 3 amps, so they're really great. But anyways, so that's the 12-volt rail. Obviously, the 12-volt fan for cooling the PDU, basically, PDU meaning power distribution unit. It's for turning on the fan for cooling the solid-state relays. The fume extractor, which doesn't exist yet, but I obviously got everything wired and even code ready for it. The fans will be 12 volts. Instrument rack cooling, those fans are all 12 volts. Those are hooked up. The PWM driver obviously is driving the 4 rails of LED lights, so that takes 12 volts. The wiring isn't exactly how it is. There's actually 2 wires. There's the positive and negative for each channel that comes out of the PWM driver. It's actually a motor driver shield, but I know that PWM can be used for lots of stuff like dimming LED lights, so that's actually what I used it for. So this isn't actually the best representation of how it's wired, but it doesn't matter. And then the buck converter steps the 12 volts down to 5 volts, and this is the 5-volt rail. So obviously Arduino is powered by that. So instead of plugging it into VIN, you plug it straight into the 5-volt pin. But you only do that if you know for sure that you have a reliable 5 volts that you're feeding into it that's regulated. This is the infrared receiver. That's the LCD, obviously also 5 volts, and then same with the real-time clock. And then the green wires are basically signal wires. This is the I2C rail. The real-time clock, LCD, and the PWM driver are all I2C, and then these are just the wires going to the Arduino, because obviously that's what's driving the I2C. And then the rest of these are just digital or analog pins to control the rest of the stuff. So that's basically reading the serial input from the IR receiver. Let's see. And then the fume extractor, I've two wires. The reason there's two wires, one is to low side switch the whole thing on or off, and then the other, because PWM pin or PWM fans, even on their lowest settings, are still spinning. So to save energy and to make things more quiet whenever I don't want them to be running, I want to be able to turn them completely off. So one pin is to turn the whole thing on or off using low side switching with a MOSFET, and then the other pin is to control the PWM speed. PD cooling, there's actually two wires now. There's the 12 volt wire, and then actually no, that would be the 12 volt wire right there. So yeah, this is good. And then that's just the basically the on or off, which is actually tied to the ground. So this is, I drew this before I worked on it today. I drew this like a week ago, so it's not completely accurate. Then I have two pins going up to the instrument cooling. One is to low side switch it. The second one is the PWM. Obviously these two wires are the controlling the two solid state relays. And then the PWM driver is obviously driving the rails. That's really the whole thing. It's not super complicated, but when you look at all the different components on here, you know, I have LED rails, PWM driver, I have a set of fans, another set of fans, another fan, solid state relays, power supply, buck converter, real-time clock, LCD, IR receiver, Arduino. And you look, there's actually quite a bit of stuff going on with such a small project, and that's why there's so much wiring. So in the future, what I would like to do and what I recommend anyone else watching this video, I'm going to try to move to some more modular connectors. Keep a bunch more on hand. That way it's just easier, because you know, I made a bunch of long wires and then hooked them into some of the daughter boards for like the ones that have fan connectors on them, basically for plugging in like the instrument rack cooling. But then when it came time to mount the project, I was like, crap, I can't put a whole breadboard through a hole just for wiring, so I had to cut the damn wiring harness, and that's annoying. But if I had a modular connector, kind of like USB, but preferably something a little smaller and a little more elegant, hell, maybe even RJ45, that'd be a good connector to use, and just run some Cat 5 or Cat. Wow, can't even get anything below Cat 5 now. Whatever's cheapest. I know phones use like Cat 3, Cat 4. Cheap network cable, an RJ45, and then just get some jacks that are breadboard mountable, and then there you go. So, and you know, that would give you 8 wires, so that'd be really awesome. But obviously you'd be limited on how much current you could send through those things. But I guess I should pull up power over Ethernet and see what the ratings are, because that could be pretty cool. Yeah, because if I had modular connectors for everything, I wouldn't have been, the work I'm doing right now to finish this up would have been a lot easier, and I'd probably be done now. But instead I had to like cut all the wires, label each one, coil them up so they're not just in a giant nest to make it neater while I'm working on it, and then soldering wires onto this for power related stuff to get this tidied up and wrapped up while all the wires are hanging off of everything was just a huge pain in the ass. I actually had to have my wife help me with soldering a few things, like, here, hold this part while I solder this, and it sucked. So learn from me, use connectors. The problem with connectors is you gotta buy tools to crimp them, you gotta know which ones to get. I don't know if you've ever looked at Molex's connector selection before, or JST. Holy crap, there's a ton, and it's really hard to know which ones you should use, or what pins go in which connectors, how to terminate them. It's just a pain, but that pain might be worth enduring if it can save you the pain of dealing with all those freaking wires that I have going on. So yeah, this time for real, I would imagine the video will be tomorrow. Should be a finished project, whatever you want to call it. and then I'll just give a demonstration to anyone strolling along not wanting to see the actual build process. So yeah, I guess that's it. I will talk to you all later.